This is the stator of a synchronous generator, right? These are your A phase winding. Let's say this is A, this is A prime, right? So your A phase winding is, let's say, wound like this on the stator, right? And your rotor is somewhere inside, and rotor has either permanent magnet or electromagnets, which is creating a air gap flux which is sinusoidally distributed, right? What it means is the flux that exists in the air gap, if this is the air gap, right, the flux that is distributed in the air gap, it's of course in this direction, it's of course radial direction, right. The radial direction flux in the air gap is given by, it's sinusoidally distributed, so you can assume it's given by B flux density is equals to some Bm cos of omega t minus theta, where you can define, let's say, this axis. So you can say this is your theta, this is your stationary axis, this is your rotating axis. So with respect to this, you will define it as theta. What it means is that in the air gap, if you want to check your B at this point, right, at t equals to 0, theta equals to 0, so B is equals to Bm. As you move away at time equal to 0, as you are increasing your theta, your B is reducing, your B is 0 here, right, again increases in the negative direction, again comes back to 0, again increases to the positive direction. So that means your majority of the flux is flowing like this, right, horizontally at t equal to 0. At t equal to t1, this whole thing will just shift, will turn. Why? How would you know? Because now the flux will be, B will be maximum at theta equals to omega t1. So instead of theta equals to 0, your B will be maximum at theta equal to omega t1. That means the whole thing is shifted, right. So the whole thing is rotating at a speed of omega. Is that okay? So this is an assumption that your air gap flux is sinusoidally distributed over the space, right, and it is rotating with a speed which is synchronous speed. Is that fine? How do we achieve it? We achieve it by either creating some different geometry of rotor, which we saw last time, right, and then that rotor is being rotated by a prime mover or a turbine at speed omega s. So that's how we would produce a flux which is sinusoidally distributed and rotating at synchronous. We will relook about the rotor structure also again later on, but for now, is this assumption okay, right? You have seen this before, induction motor, you guys have seen that the flux is sinusoidally distributed in the air gap, exactly same, and it was rotating at a synchronous speed, right? So this is nothing new, you have already seen this before. Any doubt? Any question? Okay. So if you, all of you accept this, then I think next step is that, as we did in other cases, we want to find what is the voltage induced in this turn A prime, right? And similarly, you will have B phase winding, C phase winding, so we can also derive voltage induced in those windings, right? These are stator. So stator is what actually delivers power to the load, right? So in this case, the rotor has so to say field winding, right, and stator has, so to say, armature winding, because stator is the one which is powering up the loads, which is feeding the load, and the rotor is the one which is creating the field. Rotor is the one which has created this field. So rotor windings are field winding. So rotor winding are also called as field winding, and stator winding are also known as armature. Remember, in DC motor it used to be other way around, right? DC motor, the magnets, permanent magnet used to be on stator, which would produce the field, and the load actually got connected through the rotor winding, right, which was rotating. So in this case, it's the other way around. Is that okay? Right, the terminology field winding means the guy who is predominantly making the field, and the armature is the one which is predominantly feeding the load, where the load is connected, right. Okay, now if you have the air gap flux density, right, and of course inside you have a rotor, rotor could be of different geometries. For now, let me just draw a circular rotor just to make our imagination simple. So inside is rotor, the outside guy is stator, right. If I have to see how much of flux is crossing this turn, which is like this, right. Essentially what I want to know is how much of flux is passing this vertical line. Is that okay? If I want to see how much of flux is this is one turn, right, goes inside, comes down, comes out again, goes up, right. This is one turn which is cutting the plane of the board. If I want to see what is the flux flowing through it, I need to calculate all the flux that is passing this vertical plane. Is that okay? All the flux that is passing this vertical plane is equals to all the flux that is entering from this left side or all the flux that is leaving on the right side. Because if I take integral of all of that which is coming inside, then that is what is flowing through this. Is that okay? Is that fine? So if I integrate from this point to this point, or if I integrate from this point to this point, I get the magnitude of the flux that is passing through this turn AA prime. So what is the total flux linking this AA prime? The total flux linking this or crossing this plane is equals to integral of B, L is the length of the motor, right, L is the length of the motor, d theta, let us say theta going from pi by 2 to 3 pi by 2, right, where if this is 0, so pi by 2 is this point, pi by 2 to 3 pi by 2. L is in the set plane, it is the length of the motor. Okay, where B is the flux density, so flux density multiplied by the surface area gives you the, there has to be term for radius, makes sense, R times d, right, where this is the R, right, because R d theta into L is the surface area multiplied by the flux density gives you the flux. Any doubt? Okay, now can you guys solve it quickly? Go ahead, quickly substitute for B there, quickly solve this, give me an answer. Any doubt? Feel free to ask, otherwise just calculate and let me know what do you get. L R cos omega s T. Is this what you are getting? Okay. I will come back to your question. Let's complete this. We will come back to your question. Just 2 minutes. Okay. Anyways, once you have the flux expression, if this is the flux linking one turn, then what is the voltage induced if you have n turns, right, equals to n d phi by dt or minus n d phi by dt. Anyways, we are more interested in the magnitude. So if you do this, where n is the number of turns of this AA prime winding, right, what will be E equals to? Can you now differentiate it? This whole thing, by the way, this whole thing you can call it as phi m, right, which is the maximum flux linking the turn, right. So you don't have to work with those variables, you can just work with phi m cos of omega st now, and you can calculate what E comes out to be. So E comes out to be equals to n phi m omega s sine of omega st. Is that okay? Is that fine? So the voltage induced is in A phase winding is sinusoidal of the same frequency as that of the synchronous frequency. So the synchronous generator would produce AC output voltages of the same frequency at which you are rotating the rotor, right. So it's tightly coupled to the synchronous speed. This is of course A phase voltage, let me just call it E small a. You can find the B phase voltage. If this is the A winding, your B winding would be somewhere here and somewhere here, right. So this is your B winding is 120 degrees phase shifted, whatever happens with A happens with B after 120 degrees. So you know that EB will be same magnitude sine of omega t minus 120 and EC would be same magnitude happening after 120 degree. Is that okay? So you get ABC 3-phase outputs phase shifted by 120 degree equal magnitudes, right? You use the same number of turns. Okay. Now if you find this expression you got with the assumption that all the n turns are wound just on these 2 points, right? That's why you did n times. But in reality, if you see, you cannot put n turns because each wire would have a particular thickness. You cannot put n turn in a small slot, right? So if you want to put n turn, you would end up putting few turns here, and similarly in the bottom also it will be spread, right? So therefore, for one turn the axis would be little bit more than this. For the other turn the axis would be little right side of this. So if actually they get added, the voltage induced in all of them will get added. So you will not get n times the voltage in each term because they are phase shifted, right? So imagine you are adding vectors of each of the voltage induced. They are not in the exact phase, they are slightly phase shifted. So therefore the addition magnitude will not be n times, it will be slightly less than n times, right? And therefore you have a factor called as Kw, where Kw stands for winding factor. Right? Typically Kw is slightly less than 1, which essentially takes care of the distribution of the winding. Is that okay? Kw? Visible? Not visible? Should I draw it better? 1 second. Is this fine? Kw? Okay. Just one more minute. Now this is the instantaneous value, you can write the RMS value as capital E, which is equals to the RMS of this. You convert omega into frequency, omega is 2 pi f, right? Keep everything the same, you will get the expression E equals to 4.44 NF phi m kW. You remember this expression, of course it keeps coming back, right? I mean, you have been seeing this expression right from transformer days, it just keeps coming back with slight variation. So the voltage induced in the winding, we call it E, what do you want to call it? Let's call it EF, is equals to 4.44 NF phi m kW, right? Okay, now go ahead. If you have any questions, feel free to ask. When we are calculating flux, why are we not doing what? The lines are perpendicular. This is something which again we have studied long back, right? All the lines in the air gap are perpendicular. Yeah, in this plane they are flowing some way. We are not integrating from this point to this point. What we are saying is whatever is the total flux, the total current entering this surface would flow from this side, KCL, right? So if you remember, we have drawn electrical equivalent circuits of a magnetic circuits, right, where flux behaves the same way as current. Yeah. I'm not even commenting on the direction how the field is flowing in this. I'm not even worried about that. What I'm saying is if you know the total flux that is entering here, if I keep the analogy of that equivalent circuit, right, if you know the total current that is entering here, the total current must pass through it. If it's going like this, I'm not worried. So I'm only integrating this part to figure out what is the total current entering this shell. And therefore I must take care of probably the directions here, and these are all normal anyways, right? So all of these guys are entering here and then they would some fashion go. Think over it. We don't, because we are not calculating this integration. If you would be doing this integration, then you require it. We are not doing this integration, we are doing this integration. But what I am saying is I am not worried how it crosses, because I am not integrating in that surface. Yep. Not necessary. I'm not bothered. Okay, let me try somebody else answer it. Okay, can one of you answer this question? तुम लोग बहुत discuss कर बताओ. But now he's trying to explain you. I know. Okay, you go ahead. Yeah, correct. At the in the air gap. Yes, correct. Perfect. Okay. Okay. Perfect. So there is a phase lag of a day. He had this doubt yesterday. Huh? Which guy? Oh, you had this guy. Achha, so sorry. I thought he had a doubt yesterday and today now he's clear. But today he is clear. Okay, think about it. How many of you have doubt on this part? Raise your hand. Go ahead, raise your hand. 1, 2, 3. Anyone else? 4. Okay, how many of you don't have doubt in this part? Raise your hand. Okay. What we can do is 4 of you have doubt. I can try to talk to you again. But let me give one chance to those people who don't have a doubt and see if they can explain it. So, do you want to do it? Go ahead. You have to be a little louder so that they can hear you. So we can derive the analogy from current. We suppose it was a 2D fashion of but if let's say they have to leave the same current leaves, no matter 2D similarly, if let's say the flux enter that same amount of flux will leave that surface area because these no flux lines. So those flux lines which will be passing over flux, the basic definition of number of flux lines crossing through a particular area. So if let's say we integrate the total flux, that is same amount of flux will have to cross that particular area. People problem is take to be charged that I think yeah. You have to calculate their own correct one surface area. So we will not bother to discuss कितना perpendicular जा रहा है कितना नहीं जा रहा है. We only use to integration. Yeah. Okay. Yeah. I think it's fair. Anyways, if it's still a doubt, we can discuss it after the class. But we are integrating over this surface, so we are worried about angle at this surface over which we are integrating, over which we are writing this formula, right? But we can discuss it again if still some of you have doubt. Okay, ma'am. We want to know how much of flux is linking this turn. No, I am not talking about EMF. I am just saying what is the flux crossing this ring. There is a one ring. I want to know how much flux crosses that ring. I am just saying what is the flux crossing the ring. Yeah. Of course, if this flux is there, then it's not crossing the ring. I am not worried. I am just worried about flux crossing the ring. I am worried about flux crossing the ring. They may be going like this, they may be going like this, they may be going like this. I don't know. But I am just calculating what is the total flux linking the turn. No, the flux linking the turn. Look, there is this ring, right? Now flux is flowing in this direction or flux is flowing in this direction. Doesn't matter. What is the total flux that is crossing the link or that is linking the ring, right? That is what I am worried about. So if I integrate each surface in this and I know the flux density at each point, I will get the total flux that is linking the ring. You can do anything else. It's not the exclusive answer. There is nothing wrong here. You can do it in other number of times. No problem. Yeah, but we have always been doing calculations with fluxes. We have always, like physically we have dealt with flux. Where will the EMF be induced? Okay, this is a different question. EMF will be induced in this turn A prime. This is A prime, a turn in the stator that is on which the EMF would be induced. Okay, let's move on. I think 3, 4 of you still have doubt. Maybe 1 of 2 or 2 of you have still have the doubt. We keep discussing it again. Okay, so you get an induced voltage formula which is 4.44 times NF phi m k omega. What it means is, if you just look at this EF, if I increase the current that is flowing in the rotor, what will be the effect on EF? If I increase the current that is flowing in the rotor, what will be the effect of EF? If I increase the current flowing in the rotor, inside part rotor, what will be the effect on EF? If I increase the current in the rotor, what will the effect on EF? Any guess? Let's start from there. It should increase, yeah, that's correct. If you increase the current in the rotor, your EF should increase. Next person, why is that so? Next one. Correct. So, if you increase the current in the rotor, your magnetic field density will increase, your phi m will increase, and therefore your EF will increase, right? Will the increase be linear or non-linear? Next person. Will the increase be linear or non-linear? Will the increase be linear or non-linear? Okay, anyone from these two sections, would they non-linear? Why non-linear? Yeah. Good. So, some of the things are still there. So, if I plot EF versus IF, if I assume that motor is made up of elements which will not saturate, right? So, that means if you make current double, right, flux will double because it is not saturating, right? You remember BH2, right? If your H doubles, your B doubles if it is a linear, but in reality it is not linear, it is like this curve, and therefore at some places even if H doubles, the B will not double, right? It will increase but will not double. So therefore you can relate, and you can, the B will get related to EF because B leads to flux, flux is proportional to EF. So EF is proportional to B and IF is proportional to H, and therefore the characteristics of EF versus IF. Is that okay? What do you want to call it? What do you want to call it? You used to call it something in the DC motors. What was the name? What was OCC? Open circuit characteristics. Because if you don't put any load, whatever is EF getting induced, the same EF is available at the terminal, right, at the termination of that coil. So this is called as an open circuit characteristics. So that means it will be EF times IF non-linear curve. Even if you don't give any IF, assuming that there will be some residual flux, you may get a small EF. Of course, if you give a reasonable IF, you will get a reasonable EF magnitude. And you can adjust the EF magnitude by adjusting IF current that is flowing in the rotor. Remember, even though they are both used with same subscript F, but they are not in the same circuit. IF is the rotor current. Yeah, this is little bit confusing, but since most of the books follow that, so I have also kept it the same way. IF is rotor current, right? Rotor current or the field current. EF is voltage induced in the stator, right, or the armature. So they are not in the same circuit, right? Don't get confused. I don't know why people have started using it this way, but anyway, this is there most of the books, we'll just stick to that. Any question? Any doubt? Alright. Let's look at the equivalent circuit, right, from the stator side, because stator side is what gets connected to the power grid, and all of us get the power eventually. So what is the equivalent circuit on the AC side, on the stator side? So you have, and this is of course I am drawing per phase, reality it is 3 phase. So you have a voltage induced which is EF, right, and then there is wire resistance RA or the stator resistance, you can call it RA or you can call it RS, whatever works for you, and XS. XS is the total inductance associated with the stator coil. Right. So, EF is the induced voltage, there is a series XS, series RA, and you get the terminal voltage. It's fairly simple as compared to the complicated equivalent circuits of induction motor which you have seen last semester or semester before that. Any questions so far? The XS is called as synchronous reactance. It's called as synchronous reactance, right? In some places, if you see in more detail, this is split into two components. So, XS is equals to XAR plus XL, right? What is small XL? What is small XAR? We don't want to go in too much of detail, but I will just try to give you a little bit of idea so that when you are solving problems or when you see it, you are not surprised. What is this inductance? This inductance would have two components, right? Imagine the structure of the synchronous generator, right? If you imagine this structure, now imagine current is flowing in armature, that current would lead to creation of flux. Some of that flux will pass through the rotor, right? That component is XAR. Some of the flux will not touch the rotor, will only link the winding here itself, right? That component is XL. As you can guess, XL, L stands for leakage, XAR, AR stands for armature reaction, right? Very similar to DC motor armature reaction, but we won't get into too much of detail at this point. Broadly, XAR is the flux which is linking the rotor, XL is corresponding to the flux which is not linking the rotor, but the total is XS, which stands for synchronous reactance. Is that okay? Alright. What next? Now imagine you have a synchronous generator, let's say you have a diesel generator, right? And diesel generator you want to use to feed the load in this room. So you are running diesel engine, internal combustion engine, it's rotating a shaft at a synchronous speed omega s, right? And you have given some throttle, so it's rotating at omega s, and you have this equivalent circuit, and this is feeding a load, right? Of course, it's a three-phase source. You can have a three-phase load, you can have a single-phase load distributed. We'll draw a per-phase equivalent circuit. So imagine a single generator with a single load kind of a system or a bulk load. It's not stable. This is XS, RS. What is this? This is EF. And this here is the terminal voltage, let's call it VT, right. This is how it would look like if you have a diesel generator feeding a standalone load just by itself. It's not connected to the grid, it's not a part of the grid, it's only one generator connected to some load. If I have to draw the phasor diagram for this, you guys remember the phasor diagram? This is your current flowing in the load, let me call it IL. The same current flows through these two elements also, will create voltage drops across this, and the total is EF. So if I take in phasor diagrams, you remember, right, you can take any one point as angle 0, right, and you can define all the other angles with respect to that. Again, you can take any phasor to be angle 0, but then all the other ones gets relatively defined, right. Here, let's say I assume VT to be at angle 0. So this is my VT. right? This is the terminal voltage. My load has a power factor of theta lagging. If that is the case, my inductor current or the load current is in this direction, IL at an angle theta with respect to Vt. Is that okay? Now I want to see what will be EF. So EF will be Vt plus IL into Rs in phasor terms plus IL into JXS in phasor terms will give me EF, right? So Vt I know what is voltage across, let me call it VR and Vx, right? These two drops. So what is VR? VR will be in phase with IL and magnitude will be IL magnitude multiplied by Rs, right? So this is your VR, okay. What about Vx? Vx will be lagging or leading in IL? Vx will be leading IL or lagging IL? VL will be leading or lagging? Leading, because current lags in the inductor, so voltage leads. So this is my VL. Is that okay? 90 degrees. Of course, the magnitude also you can calculate and you can draw phasor diagram with more accuracy also if you want, but this is roughly VL, this is VR. Usually VR would be small, resistance would be small. So if I have to give you a little bit realistic picture, let me just redraw it so that I can show you that VR is typically smaller than VL. So let's say this is VR, right, and the other one is VL. So what would be EF? EF vector would be equals to VT vector plus VR plus Vx. So therefore Vt plus VR plus Vx will give me EF at an angle of delta with respect to 0. Right? That's just a phasor diagram of a circuit. Again, you have done these kind of things in your first course. Any question, any doubt? No doubt. Okay, good. So now, if you know Vt, you can estimate EF and so on, right? If you know the load, because this EF is physically you cannot see it, right? It's there inside the machine. Vt is something which you can see, you can measure, right? So if you know Vt, you know the load impedance, you know the load power factor, you can try to estimate EF and so on, those kind of things you can do. But the main thing to see here is that if your load changes, right? If your load changes, if your load, you turn on few lights, you turn off few lights, if your load is variable, right? So would your, if your load is variable, then what else would be variable? What else would be variable? Of delta you mean or theta you mean? What angle? Delta, yeah. So if load is variable, that means both load magnitude can vary and load power factor can also vary depending on what you turn on and off. Then these two, the yellow vectors would also be variables which are getting added, right? Now, if you assume that you are giving the same IF and you are rotating at the same speed, E equals to 4.44 NF phi m, right? If you are keeping the same current, phi m is same. If you are keeping the same speed of rotation, F is same, right? If you assume those two things are same, then EF will of course remain the same, but your Vt will keep on changing with load. Both in terms of the angle it makes with EF, the delta will change and also the Vt magnitude will change. Is that okay? So if you change the load, your terminal voltage will keep on changing, because assuming that you are keeping IF and speed of the rotation to be same, your engine is running at a constant RPM, assuming that, and your IF is also constant. Yeah, except the magnitude of EF, in this thing everything will change, yeah. But this is something which you would not want usually, right? You don't want that एक डीजल जनरेटर चल रहा है, अभी 4 लाइट ऑन थी, 5 लाइट ऑन कर दी तो वोल्टेज कम हो गया, and then your light dims down or something slips and so on. Right? You don't want that. You would ideally want your diesel generator, if it's supplying to your house or something, you would want sinusoidal voltages of fixed frequency, fixed magnitude, 230 volt per phase. Right? You don't want to compromise that. So what do? You have some sort of a control mechanism. Right, some sort of a closed loop control which can measure the actual parameters and then take action and change your input settings or the input parameters, right. Okay, so let's say you have internal combustion engine, or it could be, let's say, a steam turbine, right, anything. It could be a steam driven turbine, or it could be an internal combustion engine which is mechanically coupled to your synchronous generator, right, and this synchronous generator has these 3-phase output, right. You can connect them in star, you can connect them in delta, so you can have 3-wire, 4-wire, whatever. So you have a 3-phase output from the synchronous generator, and synchronous generator in addition also has a field winding, which I am showing it as this, right. This has the field winding where I am supposed to feed some current IF, and the voltage that gets produced here per phase is VF. Sorry, VT is the voltage per phase, right. EF is something internal. Sorry. This is ICE, internal combustion engine, or it could be a steam engine or steam generator, or some mechanism through which you are rotating the prime mover. How do you get this IF, right? How do you get this IF? This is a DC IF, right? You may have some auxiliary AC supply, you would probably use a rectifier and then you can get an IF. Or if you have a battery, maybe you are using a battery and then a buck converter and getting IF, right? So there is some form of control mechanism which exists through which you can adjust this IF, right. IF is a DC current flowing into the rotor which you can adjust. For example, if it's a rectifier, right, you can adjust the rectifier firing of the thyristor and you can control the current that is going in IF, right. If it's a battery, you can have a buck converter or something which can adjust the IF. So in either way, this IF is controllable. The other thing that is controllable is directly you cannot touch the speed, shaft is moving very high speed, but then input to this, right. For example, what can be input to this? If it's a steam turbine, then it could be getting some form of steam, and there may be a valve, right. You can adjust the valve opening and that would lead to more steam or lesser steam. If there is more steam, more pressure, this guy may rotate faster. If it's less steam, less pressure, this guy may rotate slower. So this is one of your control parameter. This is your second control parameter. These are the two input control parameters which you have. You can control the valve, thereby regulating the speed, leading to the thereby regulating the steam that is going and hitting the turbine, or you can control the field current, which is can be controlled using some power electronic converter. Your objective is to have a fixed speed, fixed frequency and fixed voltage, right. This is your objective, or these are your outputs of this system. So you have inputs, you have outputs, you have two outputs, you have two inputs, you want to regulate both the outputs. What will you do? How will you design a basic control system? You can use yellow chalk. You can measure the voltage, right. You can calculate the RMS value, right. This will be your VT magnitude. You can compare it with your VT reference, right. You can have some G of S, some controller, whatever you have learned, lag, lead, proportional, integral, whatever you want to have, and then you can control using this. Which one do you want to control, IF or wall? Which one do you want to control, IF or wall? IF, right? Not the wall, na? Because if your voltage dips, you have an error. Even if you increase the wall, it will increase the speed, right? Which will actually lead to increase in E also, right? But that would also increase the frequency. So for this one you have a coupling basically, right? So this input affects both outputs, but IF only affects the magnitude. So therefore it is simpler if you use this guy to control using IF, and this guy anyways have effect on both. So you can use this guy to control the frequency, right? So here you use this and you control your IF. What will be plus minus signs here? Which one will be plus? Which one will be minus? VT and VT ref. VT should I do VT minus VT ref or VT ref minus VT? VT minus VT ref? VT minus VT ref. Should I do this way? Or should I do other way around? Doesn't matter, it matters, otherwise why would I ask you? Of course, you can set GOS depending on that, but let's just assume GOS is positive, right? So now can you answer which one should be doing what minus what? Okay, if we go by this one, let's say the voltage drops, so this guy drops, right? Is negative, so E is negative, it will reduce IF, further it will drop, and that doesn't help. So it should be minus and plus. Okay? Sorry? E is equals to 4.44 NF phi m. There is a F there. So if you increase the frequency, if you increase the wall, the F will also increase and E will also increase. So it has effect on both output parameters. So usually when you do this, maybe you have not done, but when you do this, any control system which has multiple inputs and multiple outputs, right? At a very basic level, first you try to identify which input has more impact on which output, and then you try to control that particular one with that one, right? In reality, there are much more complex control where you can take both inputs together and sort of write state space equations and then control both output using the together input. Have you done state space based control in your control systems? Not maybe now, maybe you are doing, I'm not sure, but there are, like, you can do it more sophisticatedly, more precisely, but as a very basic control systems, right? Simple thing is see which control affects what output, and then you adjust that to maintain that, and see which one has more impact on the other, you adjust that to maintain that, right? This is okay, this has a name, it's called as AVR. What is AVR? This whole thing which we have drawn is called as AVR, stands for automatic voltage as the name suggests, automatic voltage regulator. Yeah, you can. It's not a course more on, like, maybe you can take a some other course more on the how do you control the power delivered. So if you see roughly what happens is one way or the other it gets controlled. If you reduce the wall, right, if lesser steam sort of goes there, lesser power gets transferred, right? Lesser power gets transferred means your rotor will automatically reduce the speed, right? Proportional. That's okay. I never said that it's proportional. It reduces, right? It's not necessarily proportional. So your plant need not necessarily be linear. In fact, it's not linear here also. You see, we just saw that IF relation with VF is not linear. But we know if you increase IF, VF increases, but it's non-linear, right? So you can have non-linear controls, non-linear plants also. That's okay. But if the relationship is, if the coupling is in one direction, or rather in some zone the coupling is in one direction, you can just use that zone. In fact, here also, right, here also you can put some limiters onto the maximum IF and the minimum IF, right, so that you know, okay, in this range, right, you don't want to keep, where is that, oh, we erased it, okay. So you saw, right, B versus H graph, E versus IF, after a certain point, even if you increase IF, it doesn't make any change in the EF. So you don't want to keep increasing IF unnecessarily, right. So you can limit the values. In this range, you know that if you increase IF, your VF will increase. Not proportionally, but it would increase, right. Anyways, we have still not used this part, we will use it soon, but is this part okay? This is called as automatic voltage regulator, and remember we are talking about one generator feeding standalone loads, right. We are still not talking about grid where multiple generators are connected together, which we will do subsequently, but this part is okay. Any doubts? Okay. Then second thing, so you have managed to fix the speed, want to fix the frequency. This is synchronous generator, so N is equals to 120 F by P, P is fixed. So if you fix the speed of rotation, your frequency is fixed. So what do? You measure the synchronous speed from here, compare it with the reference speed, and use this. Have another transfer function, G to use kar liya, let's have H of S, right, and use this to control the valve. Is that okay? So suddenly if let's say you increase the load, suddenly the power drawn from the synchronous generator increases, right. You can do the same thing with IC engine also, right. I will give you an example of IC engine, that will be probably simpler to imagine. So you have a diesel generator, right, which is an IC engine. So you have used let's say motorcycles, right, and then you keep the throttle same, right, and suddenly when slope comes, right, then with the same throttle, what will happen? Naturally, your power demand will increase, so your engine will slow down, right. So if your power increases, this guy will demand more power from the shaft, this RPM will slow down. This can control the throttle, give throttle a little bit more, so that your speed again comes back to the same speed, right. So this system will make sure that your speed is always regulated to a fixed value, so that your AC output gets the same frequency. Here also you have to put plus and minus, which one plus, which one minus, something like that you can put. This also has a name, this guy here is called as speed governor, right. It sort of governs the speed or regulates the speed, so it's called as a speed governor. Any doubt? Any question? Okay, if there are no questions here, let me take slightly different topic today. We have 15-20 minutes left. I just want to quickly wrap up one topic which we left somewhere in between. I don't recall when we left, but I just want to cover it up. So any question on this? No question? Okay, then I'll just erase this part and we will just talk about a little bit about a different topic. Okay, oh, so one more thing here remaining before we move to the other topic. So coming back to the question, how do you get a synchronous flux? How do you get a sinusoidal flux distribution in the air gap? So this is something little bit we saw last time, right? We can do the shaping of the rotor, right? That was one way. The other way is that you can do the distribution of the winding on the rotor accordingly, right? These were the two ways of doing it. Do you remember when we talked about the shaping of the rotor? Is there any question on that now? You want me to explain that part again now? I can do it, right? How do you achieve sinusoidal flux distribution over the space? Let's just look at it, it will not take much time. There are two methods of doing that. One is using a salient rotor, other one is using a cylindrical rotor, right? So if you are using a salient rotor, right, If this gap between the rotor and stator is not uniform, right, that would mean that the same amount of flux will not flow through each of them, right, because there is different reluctance. You remember reluctance, right? If you have more air gap, that means more reluctance. So here bigger air gap means more reluctance, lesser flux will flow. Smaller air gap means smaller reluctance, more flux will flow. So this is one way of getting sinusoidal. Of course, you have to calculate the shape of the rotor, right? The stator is circular, this is circle or cylinder, right? This one here is cannot be a circular shape, right? We call it a salient rotor. That means it's not symmetric, it's not a circular, it's not a cylinder, right? It has a shape, right? Imagine it like a oval shape. Is that okay? So this shape actually is something like this. You have one rotor here, if you have a two pole, right, and this is where you put the winding. This is the full structure. Is that okay? This is one way of doing it. Now this guy here, because it's not symmetric, if you try to rotate it really fast, right, because of the air, it has more pressure, it feels more pressure, more drag, correct? If you are rotating it slowly, no problem, but imagine if you want to rotate it really fast, right? The structure is not very suitable for a very fast rotating type of machine, and therefore this structure is popular wherever your rotor rotates slow, such as hydro, water will come and rotate slow. Wind, you have seen the wind, anyways it rotates slow, right, doesn't really rotate very fast. But the other technologies where you are using steam, you are using gas, the RPMs are high, right, it rotates really fast. So you don't use this, you use a cylindrical one, and this is how it looks like. So this is stator and this is your rotor, right, both are cylindrical. So if your rotor is perfectly cylindrical, right, so it can rotate really fast. Let me just write down, this is suitable for low speed, and this is rotor which is cylindrical, which is suitable for high speed. Okay, does it make sense? Now the question is, if you have both perfectly cylindrical, then the air gap is uniform throughout. Then how do you produce sinusoidal flux distribution? How do you produce sinusoidal flux distribution? We have to work with different winding formation, right? One thing which should appear you to be a bit obvious, maybe not so obvious. So let's draw it, then we'll see if it's obvious or not. But let's say you have some slot here, right, and you have some turns here like this, okay. Now if I see this top half going from here till here, right, you will have flux lines like this crossing this. Will it be uniform or non-uniform? Will the flux density change over this air gap, half circle, or will it not change? You get the question? You have only turns here. This is the rotor, right, cylindrical rotor made up of very high mu material. This is your stator made up of very high mu material. In between these two high mu material, there is an air gap. Air gap is uniform. I put turns here. Will the flux in the air gap, right, be as a function of theta, flux density? Will this be sinusoidal or no? Yes. Yeah, just between these two. Yeah, that's it. I put n turns. So will B be sinusoidal? Somebody said yes, somebody said no. Okay, how many of you think yes, it will be sinusoidal? One. Somebody else. How many of you think no? 1, 2, 3, 4, 5, 6. So no. because the assumption is, and I emphasized on this part, right, here mu is very high, so reluctance is very small. This guy also reluctance is very small, only the air gap offers, let's say, predominant reluctance. If you assume that, then whether flux goes from this or any of the directions, right, it would see the same reluctance. So it's like you have multiple paths, resistances all of equal value, you would just equally divide the current among all resistances. Yes, so flux is going like this. No, turning is fine, we are not looking at turning. No, first of all it's stationary, nothing is turning. It's just stationary for now, right? We are only considering a stationary case. If we are exciting this coil, will we get a sinusoidal flux distribution? So here there is no reluctance, so flux can go anywhere in the rotor, no problem. Once it wants to cross, it would see all the crossings, all the resistances as equal. So it would just divide equally. So you will get actually B theta as a constant in the upper half and B theta constant in the negative half. So you do one more thing, you make 4 more slots, okay. Alright. Is that fine? So you put turns like this, you put turns like this, and you put turns like this. So you do this, and then you do this. Is that okay? Is that fine? To understand the geometry, you do these turns, you do these turns, you do these turns. Now the question is, will my B theta still be constant? Will my B theta still be constant? If I start from this angle and goes up to this angle, right? If I am assuming this as theta equals to 0, then if I go from 0 to pi, will my B theta be constant? No, because using a blue chalk here, consider this loop capital A and consider this loop capital B. You can see the two loops, right? Capital A and capital B. It's visible at the back. Capital A, capital B. And you apply integral of h dot dl is equals to Ni. Remember this guy, right? If you apply that, then you see the lower loop has some n number of turns, the bigger loop has more number of turns of the same current, right? So in the bigger loop, you will have larger value of S dot dl. Again, you know, the other parts mu is very large, so the primary contributor would be this path here. So in this path, you will have more B than the inner parts, right? So therefore, by putting turns, we could change the B that exists between these two turns and the rest of the half circle, right? So you could get a step change, not a sinusoidal but a step change, right? Now you imagine you do this not just with this number of slots, but you have many slots and you have like some kind of a stepped sinusoidal waveform of flux. Not perfect sinusoidal, you cannot have perfect sinusoidal in this case, which you could have had in the previous case, but you can have a roughly sinusoidal looking flux distribution in the air gap by this geometry also. The advantage here is it's cylindrical, so you can really rotate it fast. This guy has a salient pole, salient rotor structure, you cannot really rotate it fast, right? This is the maximum we want to learn about this. Of course, there are lot of other things associated with these two structures, which maybe you will learn in some advanced course. But just that these are the two popular ones. Steam turbine, you would use circular one. Hydro, you would use a salient pole one. This bigger loop will have more N into I, right, and therefore it will have more B in the air gap. The smaller loop will have lesser N into I, so it will have lesser B in the air gap. That's what. Yeah, you are right, but not in this class, in some other class. But you are correct. In this case, your reluctance changes, right? So you get something like a variable reluctance, which has its implication on torque and so on for the motor, right? This one, the reluctance will remain the same. So you remember your XAR armature reaction, which was the flux linking the rotor. That will be different in these two cases, right? Will have consequences of its own. So stator is always circular. It's a salient rotor or non-salient rotor. Salient rotor means it's not perfectly cylindrical. Non-salient means it's perfectly cylindrical. Okay, so he's saying, I have told you guys the advantage of a cylindrical rotor, right? That you can rotate it fast. But that you can use it for low speed rotation also, nobody stops you. So what is the advantage of a salient rotor? The advantage of a salient rotor is, you were saying something? You can get perfect sinusoid, you don't have to have so many slots. Frequency you want 50 Hertz, right? F is fixed. So if you have a low speed power generation, if your N is small, you have to have large number of poles. So imagine if you have large number of poles, this is only 2-pole structure. Large number of poles you will have limited surface area. Within that you have to put so many slots and turns, your sine wave will become like a really stepped square wave, right? Which is easily possible here. You can have like, this is 2-pole, you can have this kind of a structure. Yeah, 4-pole, you can have more number of poles easily. So it suits better for lower speed, higher number of poles as compared to the other one. Okay, I think we'll stop here. If you have questions, we can discuss. But you also meet me because I thought about the star question which you asked me, right? And I have some points. And of course, if that question about the flux crossing is still not clear, we can discuss now. Okay.